type of chemistry that we are dealing with percentage composition, quantities. It is a quantitative chemistry. Quantitative. There are two different kinds of chemistry that we need to know: qualitative chemistry and quantitative chemistry. This chapter, stoichiometry, is mostly focused on quantitative type. The reason why we say quantitative, because we're dealing with numbers. Every time we wanted to know the percentage composition of each element. Why we need to know the percentage composition of an element? The significance of that is, first of all, to verify the purity of the compound. Okay, let's say you have sodium carbonate. What is there in sodium carbonate? If you have sodium carbonate, what is the formula of sodium carbonate, first of all? Na2CO3. So you wanted to know what will be the percentage of sodium, what will be the percentage of carbon, what will be the percentage of oxygen. Okay, so that tells you the purity of a compound. If there is now any contaminated material, okay, that might give me some hint, some significance to understand there is no any foreign material there. Okay, so how do we calculate the percent of an element? There is a formula here. The percent of the interested element can be calculated as the atomic weight of that element divided by the formula weight or the molecular weight of the compound. Since it is percentage, it's always be multiplied by 100. Okay. In other words, if we bring this here, for example, we have we wanted to calculate the percentage composition of calcium. The percentage composition of calcium in calcium nitrate. Okay, how do we know the percentage composition of calcium in calcium nitrate? The interested elements, the element of interest in this case is calcium, right? So we know the weight of calcium is 40 from the periodic table. Divided by the formula weight of calcium nitrate, we can calculate the formula weight by adding the individual atomic weight, the weight of calcium, the weight of nitrogen, times 2, of course, right? Because the 2 is for nitrogen, and the weight of oxygen times 6 times 6. So the total formula weight is going to be written here, because percent of the interested element is going to be, in this case is calcium, is going to be the atomic weight of calcium divided by the formula weight of calcium nitrate times 100, which is 40 divided by 164 times 100. Okay, that's how we calculate the percentage composition of a particular element. Okay, if I ask you, what will be the percentage composition of nitrogen in calcium nitrate, then what will be your answer? Okay, some people say 14 divided by 164. That's wrong. It's going to be 28 because nitrogen has 14, but you have to multiply by 2. Okay, 2 times 14. That's going to be 28 divided by the formula weight of the compound, which is 164 times 100. If the percentage, if you want to know the percentage composition of oxygen, it's going to be what?
96.
The atomic weight of oxygen, which is 96, right? How do we get 96? Because oxygen has, there are 6 atoms of oxygen, let's say times 2. So that's going to be 6 times 16, which is 96. We write 96 here, divided by the formula weight of the compound, and then multiplied by 100. Well, there are some examples here that I want you to do it, but since we don't have enough time, we're going to make a discussion together, okay? Well, the point is here, it's not only to calculate the percentage composition of an element, it is also important to interpret the names of the compound. You know, in chapter 2, we studied about nomenclature, naming system. So sometimes don't expect to write a formula. It's written like this, and you have to interpret it as or you have to find the equivalent chemical formula here. It says calculate the percentage composition of chlorine in what?
Hypochlorous.
Hypochlorous acid. hypochlorous acid. Now the question is, what is hypochlorous acid?
HCl.
Hypochlorous acid is HCl. Very good. HCl. That's hypochlorous acid. So we can calculate the percentage composition of chlorine and hypochlorous acid. How do we do that? We can do that by dividing the atomic weight of chlorine divided by formula weight of hypochlorous acid, HCl, right? Times what?
100.
Times 100. That's how we calculate. How about this one here? Calculate the percentage composition of iron in what? Iron? Iron? 3 oxide. Iron 3 oxide. Now the point is here again, we need to know what is iron 3 oxide. What's the formula of iron 3 oxide? Fe? Fe2O3. How many of you agree that iron 3 oxide is Fe2O3? Not agree. Or not clear that iron 3 oxide is Fe2O3? Okay. How do we know that? The way that we know is if I have iron 3 oxide, right? The 3 here refers the charge of iron. The Roman numeral 3. Why do we use Roman numeral 3? Because iron is transition element. Iron is a transition element. And what is the characteristics, the common characteristics of transition element? They always have more than one valence. Okay, so that's why we need to indicate the charge of the transition element. So iron has a charge of +3. And oxides comes from where? Oxygen. Oxides comes from oxygen. And what is the charge of oxygen? 2 minus. -2. Because as you know, oxygen is in group 6. So the charge of oxygen is always -2. In other words, it has to gain 2 electrons. Okay? If it was in group 7, the charge would be -1, -1. Okay? If it was in group 5, the charge would be -3. Okay? So that's how it works out. So to write the chemical formula, the very easiest and simplest way is at least we can use what we call it crisscross system. So if I use a crisscross system, this is going to be Fe2O3. Fe2O3. That's why this is iron 3 oxide has a formula of Fe2O3. Okay, right? Now, what is the percentage composition of iron? What is the percentage of iron? The percentage composition of iron is going to be the atomic weight of iron times 2, right? Divided by the formula weight, the whole formula weight of the compound. Okay, which means the Fe is, I guess, 55.6 in the periodic table, maybe 55.5 or 55.6. It's going to be 56 approximately, right? So that is 56 times 2. 56 times 2 is going to be 112. 112 times what is the formula weight of Fe2O3? The whole formula weight. We multiply 2 by the atomic weight of iron plus 3 times the atomic weight of oxygen, and we add them up together. 160. So 112 divided by 160, and then what do we do? Times 100. 70? 70? Okay, 70. That is the percentage composition of iron. Now, if iron has 70%, the rest should be what? Oxygen. So it should be 30%. Without doing any calculation, you can predict that the percentage of oxygen will be 30%. If you have a condition, okay, if you have a condition that if there is no any other element involved here, that's how in the previous chapter we said that percentage composition, the significance of percentage composition is to verify the purity of the compound. You want to verify the purity of the compound. Okay? If it is less than that, or if it is more than that, this gives you an indication, this gives you a clue that there is some foreign material. Okay? Because everything has to be 100%. If so many percent has to be iron, if this iron is 3 oxide, the rest has to be oxygen, 30%. If it is less or if it is more, it is an indication that contamination is existed there. There is like trace elements will be present there. This is also the same situation here. We have calculated the percentage composition of nitrogen in calcium nitrate. Okay. Again, calcium nitrate. What is the formula for calcium nitrate? CaNO3. Okay, because you know names and chemical formulas have discussed in chapter 2, so you always need to go back to chapter 2 and to go over look the formulas, because we're not going to discuss about names. Names are a part in chapter 2. So once we know, we set up the formulas and then we can able to calculate what is the interested element. Okay? Yes.
So if we have two elements within one compound, like the iron oxide, do we need to calculate the second one, just we can subtract?
Well, you will be, okay, the way you can subtract, that's one way, or you will be asked what is the interest element. Okay, you will be asked what is the percentage of iron, or what is the percentage of oxygen. So you can answer that, whatever you ask it. But you know, once you calculate the percentage of iron, that was 70%, common sense, you can say, oh, the rest has to be oxygen.
Do we need to show the steps?
If you are asked, yes. If you are asked, yes. If you are asked to do that, yes. This is also the mole, which we defined last time. Mole means that it's a convenient measure for chemical quantities. And as I've said last time, 1 mole of anything is always have this number. This is a experimentally determined number, which is called the Avogadro's number. Now, also we discussed about the difference between molar mass and atomic weight. What's the difference between molar mass and atomic weight?
Molar mass is measured in grams.
Yeah. And atomic weight is measured in
Yeah.
mu. The difference is units. One is measured in grams, the other is measured in mu. In terms of numerical value, they are the same. The weight of sodium is 23 mu in the periodic table. So the molar mass of sodium is 23 grams. But for practical purpose, we use molar mass to do experiments. We don't use AMU, because AMU is a smaller unit, very smaller unit, very hard to measure. And the other significance of molar mass is molar mass, we can relate the molar mass with what? With what? With the number of molecules. Okay? The molar mass can help me to find out how many molecules I have in 1 mole. If I have 1 mole of sodium, 1 mole of sodium is 23 grams of sodium. In 23 grams of sodium, how many molecules of sodium I have? 6.02 times 10 to the power of 23 by definition. 1 mole of anything has 6.02, and that is numerically equivalent to the molar mass of the substance. Okay, this, for example, 1 molecule of water has 18 mu. Okay, 18 mu. But in 1 mole of water, we have 18 grams of water. You can do 1 mole of water. This is a laboratory size sample. 1 mole of water, 18 grams. In 18 grams, we have 6.02 times 10 to the power of 23 molecules of water. So this we can interpret, we can do a lot of exercises from here. I can do 2 mole, I can do 4 mole, I can do 9 mole, I can do 10 mole, I can do 250 grams of water, and I can at least predict how many molecules I have in 250 grams of water based on this relationship. Okay, since 1 mole of water is 18 grams, and in 18 grams, by Avogadro's principle, we have this much number of molecules. So you can determine how many molecules you have in 250 grams of water.
So if you times 18 times 6.02, you'll get how many molecules you have?
No, if you have 18 grams, you have 6.02 times 10 to the power 23 molecules in 18 grams of water. Because that is 1 mole of water.
That's the right mole.
1 mole. But if you have 20 grams of water, how many molecules of water you have?
20 times.
You're going to convert 20 gram into mole.
Oh,
Okay? Into mole. 20 divided
So
by
it'd be like
18.
1.2 or something.
Maybe.
And you
Yes.
times that to 6.02.
Times 6.02. Times 6.02.
So you're gonna get like,
Yes, yes. Then we're going to see about the relationship between what is the applications of the Avogadro's number in relationship with the molar mass. Okay, this is a summary of what I said earlier. Sometimes you'd be given the amount in grams. Okay, 90 grams of sodium carbonate we have. And we wanted to bring 90 grams of sodium carbonate into moles of sodium carbonate. We can't guess. How do we do that? We're going to use a molar mass as a conversion factor. Okay. If I want to bring 90 grams of sodium carbonate to X moles of sodium carbonate, what do I do? I have to find what? The molar mass. That means I have to find what is 1 mole of sodium carbonate equals to. Okay, 1 mole of sodium carbonate. 1 mole of sodium carbonate is going to be the atomic weight of sodium plus the atomic weight of carbon plus the atomic weight of oxygen, right? And then I'm going to add them up. That gives me the molar mass. So that helps me to convert grams to moles. Well, sometimes this might not be enough. Maybe you will be asked to calculate the number of molecules, how many particles, how many atoms, how many formula units you have there. Okay, so in that regard, you're going to use what? The Avogadro's number. You're going to calculate by the Avogadro's number. Okay, this is like a roadmap to explain about converting grams of a substance into molar mass. To calculate the moles, and then from moles you're going to calculate the number of molecules or number of particles. Okay. For any problems, it's not in chemistry. For any problems, how do we solve the problem? There are like guidelines here. The guidelines is that we have to analyze the problem first. Analyze the problem means you need to read the problem carefully and understand the concept of the problem. Write down the data that you're given, all the data, all the numerical values from that problem, because every number that was given are very important. And also, this is the way how you break up the problems. Identify the unknowns and the known values. What is known and what's unknown? What's known and what's unknown. Now, once you know this is like your first step. The second step is you have to develop a unit plan. In other words, you need to find a way, a bridge between the given values and the unknown values, between the given information and the unknown information, so that converging factors comes to the picture. We need to know about converging factors. Finally, once you have all the data, once you have the unit plan, and then the rest would be calculations. When you calculate, units also are treated like numbers. I have examples here because since we don't have enough time, I want you to look these examples for Wednesday. How we solve, how many moles of sodium carbonates are there in 345 grams of sodium bicarbonate. Sodium bicarbonate, sorry, it's not sodium carbonate. And I'm following the steps. It makes things easier for you. The first thing is what you need to do is write all the given values. What are the given values? 345 grams. What is the other important factor? The formula itself. That's given. Sodium bicarbonate. Okay. So once you know that, it helps you to calculate. If you know the formula, it helps you to calculate the molar mass of sodium bicarbonate, which is 1 mole of sodium bicarbonate is this much more. And the second step is look for a conversion factor between moles and grams. Between moles and grams. because we're going to change grams to moles. So we have two options here. It's a 1 mole over 84 grams or 84 grams over 1 mole. Which one we need? We need 1 mole over 84 grams, okay? Because we're looking for more. Remember, the desired unit always has to be on the top, okay? So we're going to continue this, and there are exercises here which I want you to make a practice, and then I'm going to discuss this exercise here. It's very important, okay? And then I'm going to discuss this on Wednesday.
So the question that you just did, are the moles enough like this one?
Yeah.